and then we recap what we have learned up to now briefly. So we have learned that if we make some direct replicate measurements of a parameter and we measure x1, xi, xn experimental results, we can predict the mean of further experiments like this by this writing the confidence interval, that is the average of the replicate measurement plus minus the t of the problem. The t student of the problem depends on the level of risk that we accept, alpha, the significance, number of degrees of freedom of the statistical problem, in this case n minus 1, multiplied with the standard deviation of the statistical sample, this is the statistical sample, divided by the square root of the number of measurements. And I can also write it as x average plus minus t multiplied with the standard deviation of the mean. And the formula giving us the absolute error delta x is this, and in general a statistical error is obtained by multiplying the t of the problem by the standard deviation of the parameter that you are measuring. We are measuring x average, we consider the standard deviation of the mean. Then we said, okay, we want to validate our result. We know that the expected value corresponding to these experimental values is some number, and we call it xk, where k is for known. That is equivalent to expected. And the expected value is a number that we can read somewhere. In the example of the pipette, calibrating the pipette, the expected value is written on the pipette. In the case that we determine a concentration, the expected value can be the one written in the handbook of a certificated standard for our sample. Or maybe also the value obtained by another operator who is much more reliable than us, so a reference operator. Okay. And so, in general, we have the problem of validating. Validating means to demonstrate, or trying to demonstrate, that the experimental value for the parameter and the expected value for that parameter are not significantly different. This is what we want to demonstrate. This is validation. That is not significantly different. This is the target. When we have a problem in which we compare some values of the parameter x, that is the parameter that we directly measure, we have a problem of t-test. And in the example where we compared our experimental average with the expected one, we are facing a problem of trueness. Trueness is an important quality parameter accounting for how the experimental result is, how much it is close to the expected one. This is trueness. And we said that the trueness can be assessed by a t-test. So t-test allows us to compare some results along the x-axis. This is t-test. Why I can call it t-test? Because the distribution of x can always be transformed in a distribution of t. I will plot two situations. So the one is when I plot my distribution, putting on the x-axis the parameter that I have measured. So I have already plotted it. It is this one. But we can consider to transform x in t, because t can always be written as absolute value of x minus x average divided by s of x average. So x and t are equivalent. They are equivalent. And in fact, that distribution can be replotted, putting here t, and here the probability, and here we have t equal to 0, 0 distance with respect to the average, and t goes from 0 to infinity. Okay? This is the t-test. That's why we have defined tk, that is that value of t that is identifying the position of xk. So we said, instead of using the number obtained, the number corresponding to xk, we want to use tk, corresponding value of t. And we want to compare it with the t tabulated. The t tabulated is the one that we use for calculating the borders of the confidence interval. So this parameter is briefly called by me t tabulated, because I can obtain it by consulting the tables, statistical tables. Okay? So, okay, we have drawn t tabulated in green because it is corresponding to the experimental value. It is useful to use the color code. So t tabulated comes from experimental measurements and experimental choices, because it depends on me, and me depends only on the number of measurements, but alpha is depending on our choice. Theta is the reference for tk. And we said, if we obtain that is lower than t tab, means that xk is inside the confidence interval. So we say there is no significant difference between xk and x average. And when we have the case in which tk is higher, then there is a significant difference. We also said using this subjective comparison may be risky, maybe not so clear to be understood. So we prefer to quantify tk by the p-value. And the p-value is the tail corresponding the external tail, and it is symmetrical, corresponding to tk. So in red we have the p-value, while in green we can visualize the tails of the confidence interval. So suppose that the confidence interval is here. So here we have x average plus t tab multiplied s of the mean, standard deviation of the mean. This is the right border of our confidence interval. And so we can see that alpha is the area, external area, corresponding to the boundaries of the confidence interval. So in green we have alpha. When p-value is higher than alpha, means that xk is inside the confidence interval. So we conclude the same as we conclude when tk is less than t tab. So we can write this equivalently by writing p-value higher than alpha. Okay. I have the doubt, did I start? Yes, I started. Sorry, sometimes I'm so. Okay. So this is what we have found. This is equivalent. In the case that the higher holds true for t, the lower holds true for p. And this is what we concluded. And we said that using p-value is useful because it is a parameter ranging from 0 to 1, that is a degree of similarity. It is more intuitive. Moreover, we can directly compare the p-values of very different measurements, of operators measuring different parameters, also with different techniques, because p-value is the closeness to the expected value. Okay, now we move forward and we said, okay, but I can have the problem to compare my confidence interval with a single numerical value. But I can also have the problem of comparing two confidence intervals. So suppose that I am operator 1 and I measure a parameter x by direct measurement, and I obtain x average 1 with a variance s squared 1 and with degrees of freedom and μ1 that is equal to number of measurements that I perform minus 1. And suppose that I have a reference value obtained by a very reliable method, and it corresponds to x average 2, variance 2, degrees of freedom 2, (2). So, in this problem, the reference value x is x average 2, which is the reference value. And I am true, my trueness is good if my average, x average 1, is close to x average 2. This is trueness. So I can say that comparing these two values implies to perform a t-test. So we have to calculate tk and think about what it means and how it is calculated. Of course, it will be calculated with a little bit different formula with respect to the case where we compare a confidence interval with a single value. But it is a t-test. While if we want to compare two variances, we have to perform a test called F-test. F-test means test of Fisher, and Fisher is a scientist who faced the problem of comparing two variances. Now let us think about this issue in a general way. So let us ask, if I could measure all the possible values of the ratios of these variances, which distribution could I observe? So, in a general way of reasoning, of discussing, we define F, Fisher parameters, as variance 1 divided by variance 2, and at the beginning we make no hypothesis about being S1 higher or lower than S2. So we consider the general case. And if we perform ideally, an infinite number of experiments in which S1 and S2 have infinite degrees of freedom, mathematics allows us to calculate the function that expresses the probability as a function of f. So we write down, we plot a statistical distribution where on the x-axis we put all the possible outputs in measuring f. And in the ordinate, the probability of observing those values. And now I am asking to you, which is the range for this general parameter, no matter whether the numerator is higher or lower than the denominator, in general.
From 0 to plus infinite.
Exactly. So the function covers all the positive axis of real numbers. And the trend, the plot, is this. It is asymmetrical. Which is the value of f? Yes?
Can you repeat why is this asymmetrical?
Because the function found by Fisher has this trend. So in order to explain it, you should write down the equation. It's very complicated equation, and it is like that.
Okay, thank you.
Now I ask you a question. What happens when S1 and S2 are identical? Which is the value that we observe? Unity 1. Do you think that it is different, the probability of finding S1 higher than S2 with respect of finding S2 lower than S1 lower than S2? I have two cases. The first case is S1 higher than S2. And the second is S1 lower than S2. Okay? Do you think that they have different probability?
No.
No. So, if I write here F equal to 1, do you agree that the area on the right and the area on the left are the same? But the total is 1. So I know that the area in both the tails is 4.5. You agree? Now, analytical chemists are very strange people because they don't like to have S1 lower than S2. So they calculate F putting always the higher variance in the numerator. It's the choice. Why they do this choice? So they define F, K as the higher variance divided by the lower one. There are two reasons for this choice. One is empirical and one is mathematical. Empirical choice. Chemists are interested in the lowest variance as possible because having a low variance means high precision. So they are not interested in asking whether the two variances are different. They are interested in assessing whether the minor variance is significantly better, it is lower. Okay? They are looking for high precision. So they are looking for the lowest variance as possible. That's why they make this choice. It means that analytical chemists will explore only the right tail. So this, the only tail explore, only tail explore in analytical chemistry. Okay? Is it clear? Because we always put the higher in the numerator. So F will be always higher than 1. I have to make order in my slides, okay? So this number is always higher than 1. Really, it could be equal, very improbable, very improbable, but it could be. Okay?
So, sorry, Professor, but we calculate this ratio several times, making ratio between an higher variance, whatever it is, at the numerator, and a lower variance at the denominator.
I did not explain that. So your question tells me that I was not so clear. So I repeat, this is the case, ideal case of infinite measurement.
Yes.
But I am performing a finite number of measurements. Okay? So this F, the F calculated by me comes from my experiments. While this plot is the ideal population of all the possible cases. But I can think about comparing the distribution of the population. This is the F distribution of the population. I will write this. This is infinite number of measurements, and this is the F distribution of the population. The population are all the possible values. Okay. Now I'm going to compare my measurements, real measurements, finite number of measurements, with the population. The same that we did with T. Because here, in black, you have the population. And in green, you have numbers coming from a sample, statistical sample. The same way of thinking about this problem and getting a conclusion. Okay? It's very similar. I know it is a very theoretical way of reasoning, but it is what leads us to understand the problem. Okay? Are you okay?
Yes.
So, now I want to compare my FK with the F tabulated.
Sorry, Professor, we mentioned the empirical reason for which...
Oh, sorry, thank you for the question. The mathematical reason.
Exactly.
You see that in the right tail of this distribution, to each value of P does correspond only one value of F. Okay?
Yes.
But if you go here,
No, in the right tail?
in the right tail,
Yes.
one value of P, one value of F. But here, one value of P, two values of F. It's a possible conclusion. So this is a mathematical reasoning. The mathematical reasoning. And that's why when we will perform the Excel exercise to calculate F, the Excel will propose us automatically the F calculated in the right tail. Because from the mathematical point of view, it is more coherent. One value of P, one value of F. Okay? So we stay on the right tail for two reasons. Because we want to find the lowest variance, and because we want that one value of f corresponds to one value of p.
But from 1 on?
Yes, from 1 on. It is the right tail. The right tail is this. This is the right tail.
Because I will say that the lowest variance is minor than 1.
We put fk, we define fk with the numerator.
Yes, I know, but so the choice is to find the lower variance, but starting from 1.
Starting from f equal to 1. F equal to 1 means that S1 and S2 are equal.
So we want f to be as similar as 1 as possible. As
Yes.
close as 1. Okay.
Yes, yes, this is the target.
Okay.
Okay. We choose to put the higher variance in the numerator. And our target is that the two variances are equal. So the target is that f is 1.
So, Professor, maybe I'm getting confused because I didn't understand if with fk we use the higher, an higher value or the highest, like the highest possible
okay.
and the lowest possible.
No, higher when comparing S1 and S2. The higher of the two values. Because
So we have only two values. No.
okay, I will try to listen. Okay. F is variance 1 divided by I use these two cases. Okay. Okay, how do I calculate it? If S1 experimental, my result x1 is higher than S2, then I decide to calculate Fk as S1 squared divided by S2 squared. Okay? But if S1 results to be lower than S2, then I decided to calculate Fk as S2 squared divided by F1 squared. This is the choice. Okay? Is it more clear now? So I consider these two numbers.
So we have two sets of measurements and
Yes.
we have the variances of the two sets.
Yeah, the problem is this one. Okay.
Okay, yes.
So I measured experimentally the green series of numbers, and some extremely accurate operator measured the red one. I wanted to compare my variance as a square 1 with the other variance as a square 2.
Okay.
And they are two numbers. Okay? The highest numbers of the two is in the numerator. Maybe you are right, I should write here highest. Of the two, highest of the
Okay,
two.
now I understood.
High, low. Let's write like that. Is it clear now?
Okay, and we obtain
A number.
parameter.
Fk that is always higher than 1.
But if it is, for example, 1, the two operators work very good.
Well, with exactly the same variance.
Okay.
And this is the best case for me.
Okay.
Because I want to demonstrate that my precision is as good as the precision of the reference precision. This is the target. So I desire to find Fk equal to 1. Okay?
Yes, thank you.
So F is a ratio and the target value is 1. Okay?
Okay.
So now I will plot again.
Sorry, Professor,
Yes?
can I assess the lowest variance also if I not consider the mathematical reason, just consider the empirical reason? Can I assess the lowest variance also if I decided to consider always Fk equal to the lowest over the highest?
Yes, you could, but there is a mathematical problem.
Okay, it's clear. Fantastic.
So we choose the right.
Okay, fantastic.
Okay. So now I plot again the distribution of F, so the population of all the possible values of F that could be observed, something black. All the possible values of F, the distribution of F is this, and I explore only the right tail. Okay? In the previous, I did not write that area, right tail, equal to 0.5, 50%. Okay? This is the maximum area. Okay, this is the population of F. And I can drive my Fk. Okay? The Fk obtained from the results. Maybe it was better to use the green, because Fk. This is the observed value from experimental values, and the reference one is corresponding to the level of risk that I choose. I don't know. Okay, let us leave the colors like that. So we have delete the last word. Okay. Now somewhere there is the ratio of the two variances that is obtained by my experimental values compared to the one of reference. So here we have Fk. And the best situation is when Fk is close to 1. Now, Fk comes from a simple ratio of the two variances, and I can ask what is the meaning of this area. So let us consider
the p-value.
Yes, exactly.
What
What is the meaning of this red area? And the correct answer is the p-value of F. And it is the degree of closeness to the target value of 1. In fact, when the two variances are equal, so when S squared high is equal to S squared low, we have Fk close to 1. Do you agree?
Yes.
So if fk is exactly on the value 1, p-value is 50%. 50% because the area in the right tail. So p-value tending to 0.5. And the conclusion is same precision among the two operators, the same. If S low is very, very, very lower than Si, so you have that F tends to infinity. Fk tends to infinity because Fk is S high divided by S low. Okay. And the p-value is
0.
this. Okay. So p-value is ranging from 0 to 1, sorry, 0.5. So F, K, let us say directly p-value of F right tail ranges from 0 to 0.5, and this is where S high is enormously higher than S low. And this is when S high is identical to S low. Of course, in this case, I should write S1, S2 because they are identical. None of the two is higher. Okay, S1 is identical to S2, and the ratio is 1. Okay, this is the way of getting an objective decision.
Sorry, Professor, normally we indicate the variance just with S.
S is the standard deviation, of course. If S is equal, if S1 is equal to 2, also the variance is R. Okay. It is equivalent to compare the two.
No, it's just for the notation.
Yeah.
I always have to write the variance as S squared, right?
Yeah. The variance is a square. The variance is the square of the standard deviation.
Yes.
And in statistics, it is useful to use variance because variance is additive. I mean, if I make 10 measurements, I have some variance. Then I make further, say, 5 measurements, and I calculate the variance. The total variance is the sum of the two.
Yes.
Variance is additive. So when a statistical process,
The standard deviation is not additive.
it is always additive.
So why we don't use this? Why we use the variance instead of the standard
Because
deviation?
standard deviation is not additive. Variance is.
Okay, so standard deviation is not additive.
No. Sorry, I didn't understand. Variance is always additive.
Okay.
Standard deviation, no, because you have to square it. Okay. I will explain, I try to explain better. So I take some measurements of X. And at first I take X1 as to X10. And from these I calculate S squared 1.
Yes.
And then I decided to go on and measure X11 up to X15. And from these further 5 measurements, I decided to calculate S squared 2. We are talking about S squared of the means, okay? And if I wanted to consider the 15 measurements as a sample, the the variance of the mean, 15 measurements is equal to the variance of the mean for 10 measurements plus the variance of the mean for further 5 measurements. Of course, it is correct for the square, not for the square root. Okay? Okay? Because the square root of this is the square root of the sum, which is not the sum of the square root. Okay? S, the mean for 15 measurements, is equal to the square root of S squared of the mean for 10 plus S squared for the mean for further 5.
Yes.
So it is not true that S for 15.
Okay.
So the variance is additive. The square root of the variance is standard deviation. It is not. It is useful. Why? Because variance is variability. And I think you will start multivariate studies. Have you already started to study multivariate statistics?
No.
I think you will study in the next year with Professor Schuto. And in the case of multivariate analysis, variance is information. So information is useful when it is additive. Okay. That's why we use variance and not standard deviation for calculating F. Okay? So let's go back to this. Okay, the p-value is the degree of closeness of fake fk with respect to 1, but we can consider the tail, the right tail, containing the significance alpha. That is, somewhere here, the tail corresponds to alpha, significance. And the value of f corresponding to alpha, we call it f tabulated. Okay? This is analogous to the choice for T. What is tabulated corresponds to the risk of error that I accept. And p-value is the effective closeness of the two compared values. Okay? So if I look to this situation in this plot, I see that fk is closer to 1 than f cap. Okay? You will be with this sentence. And you can understand what I'm trying to communicate, if you make the analogy with the t-test, the analogy. Let us try. You see this situation for t-test. So the tabulated value corresponds to alpha. The p-value corresponds to the expected value in this case. Okay? And you see that p-value is higher than alpha. So when we move to the f-test, we should try to make an analogy. So the degree of closeness of fk to 1 is higher than the minimum that I accept, that is alpha. In this case, I conclude that the two variances are not significantly different. I want me to have you, all of you, understanding what I'm trying to tell you. Because this is a crucial concept. There are few basic concepts in statistics. In univariate statistics, there are few. They are degrees of freedom, variance, p-value, and few others. So I want you to understand the meaning of alpha and p-value. Have you some questions?
No, just the conclusion, in that situation, the two variances
are not significantly different because the closeness of fk to 1 is higher than this distance corresponding to alpha. It is more close, so it is better. No? Okay? Shall I go on? So, I can state subjective precision, subjective capital L. When fk is less than f tabulated, meaning that f tabulated, then the correct statement is no one of the two variances is significantly higher because I have performed a one-tailed test. But this implies that they are not different. So, no one of s square 1 and s square 2 is significantly higher or lower is the same, then it implies that s squared 1 and s squared 2 are not significantly different. So I can say, okay, my precision is comparable with the reference precision, I am happy. And the same conclusion comes from the case that the p-value for f is higher than alpha. Okay. Now we can generalize the p-value and then we'll take a break. And then we moved to the t-test because we have still to do the t-test for this case. For this case, we have considered the f-test, but we have to consider also the t-test. Okay. So, the general definition for p-value is the degree of similarity of the measured value, experimental value, with respect to the median of the distribution. Why I say median? Because in the case of F, it is asymmetrical. So we have 1 point, F equal to 1, where the area is 50% and 50%. In the t-distribution is symmetrical. So the median is equal to the average, to the mean. They are coincident. Okay? But in general, p-value measures how the reference value is coming close to the median of the distribution. P-value is high when the red value is close to the green one in the t-test. In the f-test, the p-value is high when the red value is close to 1, to unity. Okay? There is a little difference, but in any case, p-value is a degree of similarity of what we hope with respect to what we have to compare. This is p-value. Sorry?
No, because we said that it is a degree of similarity of the experimental value with respect to the median of the distribution. But in the t-test, the median of the distribution is an experimental value.
Yes, there is a little difference between the two distributions. You are right, because in the t distribution, in the median, I have the experimental average. While in the F distribution, in the median, I have the target value 1. Anyway, I want the red value to come close to the median. In both cases, I want the red value to come close to the median. TK close to the median, X average, and FK close to 1, the target.
Okay.
General definition. Anyway, you see you have a p-value for t-test ranging from 0 to 1, and the p-value for f-test ranging from 0 to 0.5. But the meaning is similar. When I get close to the median, it is okay. Okay? Now we take 15 minutes break, and then I will explain the t-test for this comparison. Okay? If you want to reduce the break, tell me.
No.
If you prefer, because we have started late. So timing. If you want only 10 minutes, I think I can make 5 minutes, 10 minutes, as you want. 10 minutes. Now I make a break in recording. Finish complete my explanation in this way. F tab depends on the FK, on alpha, F tab depends on alpha, and on μ1 and μ2.
Okay.
So we are comparing these two series. F tab depends on alpha and on μ1 and μ2. We will learn how to calculate F tab by Excel. I can anticipate it. There is a function. So F tab is F dot INV dot right tail, and it asks for alpha, μ of the numerator, μ of the denominator.
Okay, thank you. No, I just wanted to be sure of like if we had to choose that like alpha or
Alpha is chosen by us.
Okay,
Yes.
it depends on it. Okay.
And in general, we choose 55% in general, but it's not necessary.
Okay.
Professor,
Yeah.
FK is an experimental value.
And K in this case is experimental because it comes from the ratio of the two variances measured. Yes.
Okay, Professor, if you want, we can skip the break and
Skip,
finish.
okay,
Yes.
go on. Okay. So we try to finish the lesson at 1 p.m. Okay? Okay, now we have to define the TK for the comparison of the two average values. There is a formula, and according to my experience, if I write the formula, students understand nothing. So I have learned to make the students obtain the formula together with me by analogy. That is, I compare the two cases. Okay, analogy. We are using our brain to obtain a formula by analogy, the formula for TK. Okay, when we compare a confidence interval, so what we studied yesterday, so we compare the confidence interval of the mean, so it's average plus minus beta multiplied as standard deviation of the average. What did we write? We wrote TK equal.
Sorry, when we compare confidence interval of the mean with
With a known value of K. Compare with, I don't know this time. With xk. Okay? Okay, we wrote here x average coming from our measurements, experimental measurement, minus the expected value in absolute value. And we wrote S divided by square root of n. Do you agree that it is equal to writing square root of S squared x divided by n? It's the same.
Yes, of course.
It's the same. Because this is equal, I would write here, to Sx divided by square root of n. The same. Okay?
Yes.
So written in another way. Why did I wrote like that? Because do you believe that this is the variance of the mean?
Yes.
This is the variance of the mean. True? Is it true? now we make the analogous with comparing two confidence intervals. That is x average 1 plus minus t, let me write simply t1, okay, t for the first case, multiply s squared x average 1, okay, we compare this with x average 2 plus minus t2 multiplied s squared x average 2. Okay? And this is green, our experiment. And this is the red, the reference confidence interval. So we know that the red confidence interval is perfect. It is our reference result. And we want to state whether our average value is or not significantly different. Okay? I go on that slowly, step by step. Is it clear for you? Now, try to tell me how the formula of the left is generalized. Remembering that variances are additive. Okay? So now we have tk equals, this is some absolute value of a difference, and in the denominator we have some variances. Okay? On the right, which is the analogous of x average of the left? Yeah. So it is x average 1 minus x average 2. Okay? And below? On the left, I have only one variance. On the right, many additive variances. Please tell me, what one should I write?
S squared average 1.
Yeah? Sorry, because you use another color, otherwise it could be confusing. So, S squared average 1 divided by and 1, because each of the two operators has its own number. And 1. And then plus S squared x average 2 divided and 2. Done. This is the formula. Yeah.
Shouldn't we, in the confidence intervals, have the standard deviations and not the variances?
It is the same, because the variance of the mean is the variance of the single measurement divided by n. I mean, in general, I will write it here, this S squared x average is equal to S x squared, the one written above. Okay, it is already written. This is the square of this.
No, I mean in the two confidence intervals on the right. I don't understand why we have the.
I have written S square of the mean one.
Yes.
That is S1 divided S1 squared divided by N. Is it something wrong with my formula?
No, sorry, Prof. I couldn't follow, honestly.
And this is the doubt. Could you?
I don't understand why we have the square.
Here?
Yes.
Okay, let us consider in general a confidence interval of the mean. The confidence interval, I'm sorry, I think that you are right. You're right. Because we should put the square root.
Yes.
It's right. Thank you. Okay. That's okay. You're right. That was the doubt. The square root was missing because I am multiplying t by the standard deviation, not by the variance. It is correct. And in fact, okay, in order to make the analogy to the left, where I wrote S of the average, I could write also on the right S of the average. For uniformity, it is the same, of course, it is the same, but it is easier to write like this, and like this. Okay, now it is okay. Because T should multiply the standard deviation. And we use variances because they help us to obtain easily the extension of the formula. Okay? Okay, now we move to the other, we move to the conclusion. But before concluding, according to you, I should compare TK with what? Because in the case of comparing the confidence interval with a single value, TK was compared to T tab.
Yes.
And tab was corresponding, T tab was corresponding to alpha and me. There was only one number of degrees of freedom in this problem. Okay? So here I have a number of degrees of freedom that I have called me. Only one value of me in this problem. But when I go here, you see that I have two number of measurements, and 1 and 2. So I have me1, me2, but I have two parameters. It's average 1, it's average 2. So can you help me to calculate the total number of degrees of freedom on the problem on the right? Total number.
So we still compare TK with T-tab also in this case, but now we are calculating T-tab due to the fact that we have 2 degrees of freedom.
Yes, T-tab always depends on alpha and the number
exactly,
of degrees.
Alpha is always.
Alpha is chosen by us. But the number of degrees of freedom involved in the problem depends on our measurements. So, since the variances are additive, could you be confident that I am right in saying that also degrees of freedom are additive? So I must sum the 2 degrees of freedom. Do you agree? So it is μ1 plus μ2. And it is equal to the total number of measurements, that is n1 plus n2, minus 2 because I have 2 averages considered. Okay? So it is coherent. So when we perform the t-test for comparing 2 average values, the t-tabulated will be calculated as by itself as t dot r and b dot to t, and alpha is chosen by us. μ1 and μ2 are the total number of degrees of freedom. Because the number of degrees of freedom is concerning the problem. So we should compare tk with the t tabulated, calculated by this way. I can finish my explanation considering that the formula that I have wrote here can be simplified when the F-test is passed. I mean, consider this example.
I just understand when the F-test
Is okay.
Oh, it's okay.
But the F-test is okay. So, consider this example. One operator performs 10 measurements. The other one performs 5 measurements. So I can make an F-test on S square 1 and square 2. If the F-test is passed, means that they are not different. Okay? Maybe my English not so perfect. So, F-test is okay. It does mean, you see, the 2 balances are equal, are not significantly different. But if this is true, if it is true that S square 1 and S square 2 are the same, means that there is a single population to which all the 15 measurements belong. There is a single standard deviation or a single variance representing the 2. And this single variance, so we are considering the case that S square 1 I want black. Okay, sorry. We consider the case, so when S square 1 is not significantly different with respect to S square 2, there is a single population to which all the N1 and N2 measurements belong. And the variance of this single population can be calculated from S1, S2, μ1, μ2, because it is S squared of the population, of the single population, equal to μ1 multiplied S squared 1 plus μ2 multiplied S squared 2 divided by μ1 plus μ2. So in this case there is a simple formula.
No, for me it's absolutely not clear.
Okay.
Where,
okay, I will explain in another.
No. Let's see.
Okay.
Okay. Well, okay. Understood that there is a single variance because, of course, they are not significantly different, representing the two population. But there is a single population.
There is a single population to which all the measurements belong.
Okay, but all the measurements. Okay, so
of the first operator and the second.
Okay. So all μ1 and μ2. Okay, and
yes.
so here we have written that the variance of the population.
In this case, the variance of this unique population can be calculated from the data of the problem. From S square 1 and S square 2, and from μ1 and μ2. This is a theorem, I cannot demonstrate it. But it is
Okay, so it's just to say that we can calculate the total variance using this formula.
Using this formula.
Okay.
Because this formula is an average, but it is a weighted average. A weighted average, where the weight, the statistical weight, are the degrees of freedom. So in this case, when the two compared variances are not significantly different, we can simplify the formula. So I will write the general formula and you can tell me how does it simplify.
Okay. Sorry, we are weighting the single total variance for the two different variances.
Yes.
Okay.
Yes. The total variance is calculated as weighted average,
Okay.
and the statistical weight are the two degrees of freedom. Ok?
Sì.
Okay. Media pesata in italiano. Media pesata. So,
it's not important, just.
okay. It is a definition, and it is easy to understand it. If you try to consider the case where μ1 is equal to μ2. Okay? What does it happen to the formula? When μ1 is equal to μ2. I will write here. So the general formula for S square P is μ1 multiplied S square 1 plus μ2 multiplied S square 2 divided by μ1 plus μ2. Suppose that μ1 equals μ2 equals v. It is possible that the two operators make the same number of measurements. Okay?
Yes, my doubt is the fact that also the two variances are equal. Is that
they are not significantly different. It is not exactly the same statement because they are identical only when f is equal to 1. Otherwise, they are not not significantly different, so it is a subtle difference in the two cases. Okay. When S1 is identical, yes, of course, but they are slightly different, not significantly. And what does it happen when we have μ1 equal to μ2? It happens that S square P is μ multiplied S square 1 plus μ multiplied S square 2 divided by 2μ. And so it is the arithmetic average in this case. So this formula is a weighted average. Anyway, this is a subtle definition, is not important. Now I want to generalize the formula. To simplify. The general formula was Tk equal to x average 1 minus x average 2 divided by S square 1 divided n1 plus S square 2 divided by n2. Okay? Mm-hmm. If S1, S and X2 are approximately equal, I can describe them as P. So x average 1 minus x average 2 divided by SP squared divided by n1 plus SP squared divided by n2. Okay? I have used S square P as calculated before. I will repeat here. Okay? And then it ends like that. Tk equal to x average 1 minus x average 2 divided by Sp multiplied by 1 over n1 plus 1 over n2. And this is true when S square 1 and S square 2 not significantly different. It is a simplified formula, okay? So, in order to complete the comparison of the two series of measurements, we performed two tests. I will write again because it is useful. So, the first series was x average 1 square S1 square μ1. The other one was x average 2, variance 2, degree of freedom 2. And we said that we performed a test for this, an F test for this, and then we said that t-test corresponds to analysis of trueness. Variances account for precision. When we perform both a test of trueness and a test of precision, the analytical mechanists say that we perform a test of accuracy. So, a measurement is accurate if it is both true and precise. This is accuracy. Up to the previous century, accuracy was confused with trueness. But since 15 years ago, the International Conference on Chemistry decided to specify trueness. You have trueness when your average value is close to the expected. You are precise when your variance is low. You are accurate if you are both true and precise. Okay? This is a development of the definition of accuracy. When I studied for my graduation 40 years ago, we had a text, a book by Miller, and it is still the Bible of statistics. And in the old version, trueness, accuracy was defined as trueness. But now we want to specify accuracy is more than trueness. It's trueness and precision. If you want, I have the original article in which the International Union of Pure and Applied Chemistry defined accuracy. If you want to make an accuracy test, you should perform both a t-test and an f-test. Okay? In the afternoon, we will make an exercise, and in this exercise, I have chosen to consider the easiest case when the two variances result to be not different, so we can manually calculate the f-test and the t-test. And then I will show to you that Excel has a function which automatically performs t-test and f-test. But we will start by manual calculation in order to understand what we are doing, what we are calculating, why we should compare these two quantities, why I should take the total number of degrees of freedom as the sum of the two numbers. So we will do this in the afternoon at 2 p.m. Okay?
Yes, Professor, can you just repeat please the definition of true? Where true if our measure is
close to the expected one.
Trueness.
Yes.
Instead, precise if our variance is low,
Yes.
and accurate of course if low.
Both. Yes.
Thank you so much.
Trueness in this case is when the green mean value is close to the red, but the red one is the reference value. So if my experimental value x average 1 is close to x average 2, I am true. And if I am also precise, I am accurate. It is not clear?
No, I probably remembered wrong because I was convinced that accuracy was the closeness to unexpected values, but I switched to the...
In the past, accuracy was confused with trueness in the past definition. But now we define accuracy as both trueness and precision.
So precision is measurements that are close to each other.
Yeah.
Trueness is the closeness from between measurements and unexpected values. And accuracy is both.
Is both, yes.
Okay.